So where they should have picked up last class, and we can verify this. They had finished. They had done. We'd done the single displacement and we'd done the double displacement. We started off with the dissociation. So, is it okay for me to pick up there? Okay. So, anyone has questions? I'm just going to start going through what we picked up. So, dissociation involves what kind of compounds? What kind of compound is that? So, you've got a metal here and a non-metal. Ionic compounds dissolved in water. Water is the solvent. Only change is, so look at what it starts out as. It starts out as a solid, ends up as an aqueous. Did I change what the stuff was? No. So the only change is the state of matter. Okay, and then he gives us a couple equations here to work with and balance them. So under dissociation reaction, you're starting off with this salt. Now, when you're dissociating, you do not add water. Okay, water is not a reactant. It's understood that water is used to facilitate the process. So it's just a reaction. And the charge on this aluminum here is a +3. Once it now has a charge, it's an aqueous salt. Now you've got 3 of these nitrates that you got to keep track of. The easiest way to do that is when you break them into one piece like that, you're going to bring that 3 back in front of that nitrate, and that's going to stay aqueous. Now, if you were to do the ammonium bromide down here, you did the same thing, but now ammonium is acting as your metal and bromine is acting as your non-metal. So it breaks apart into the ammonium and the bromide. Have to have your aqueous, have to have your charges. Okay. Now for your calcium part, it's going to do the same thing. And then your, I'm not going to do the MgOH2 because it's going to look exactly like calcium. It's going to have the same charges and everything. Okay. The 2 that most people get confused is dissociation and ionization. Dissociation has nowhere on the left side of the equation do you see water. Okay, there's no water over here. It's just the salt, and all you see on the right is the aqueous, what it's producing in the charges. Okay. So you've got some columns of strong bases here. So anything that is in the lithium column, so it's hydroxides of lithium and everything below lithium. So that's lithium, sodium, potassium, rubidium, cesium, and francium going down that group, except hydrogen at the top. Those are going to be strong bases. Your other strong bases start at calcium and hydroxides of calcium and every guy below it. You do not include magnesium hydroxide or beryllium hydroxide. Okay, magnesium and beryllium hydroxide is not strong bases. But calcium hydroxide, strontium hydroxide, barium hydroxide, and radium hydroxide are. Okay? So this is your trend for remembering your strong bases. So if these are your only strong bases, then everything else besides your strong bases that you've been told is a weak base. If it's not a strong by virtue, it has to be a weak base. Okay?
I have a question.
Mm-hmm.
How do we know if it's strong or weak?
These are the only strong ones.
These are okay.
That's it. It's the only strong ones. If it's not a lithium hydroxide in the column under lithium, and it's not a calcium hydroxide and in the group 2 column under calcium, it's not a strong base. So what about this one? Strong or weak?
Weak.
Weak. Because this is an iron hydroxide. Even though it's got a hydroxide on it, all it's going to do is get it a base. But that iron is in that group 3D10 group, so it's a weak base. Any guy out beside that, any other metal besides those 2 columns there, starting at those very specific points, is going to be weaks. For the very same reason that you got 7 strong acids, sulfuric, or chloric, hydrochloric, hydrobromic, hydroiodic, and nitric. These are your only 7 strong acids. And if it's not one of these 7 strong acids, it's not a strong acid. Okay? So if you give anything else that has hydrogen out in front, what about this? What about HF? Strong or weak? Weak, right? But it's not in your Strong's list. So anything else instead of trying to remember all of them, just remember the strong ones. If you know the strong ones, or you can at least find the strong ones, and everybody else is weak. Okay?
And is there which one's stronger, or are they all the same?
When you get to Chem 2, what you'll find is all of these follow what's called the leveling effect. So in equal molar ratios, they're exactly the same, except for that guy right there. If you look at the rest of these only have 1 formula unit of hydrogen. This guy's just a little bit stronger because he has 1 formula unit of hydrogen that he can react the first time, and 1 more formula unit of hydrogen he can react the second time. So this guy will be slightly more acidic, and therefore slightly more powerful. That's why we actually use them in battery acids. So battery acids in your cars is sulfuric acid mixed with water. This is a little bit stronger, produces a little bit more energy. Also means it's a little bit more corrosive. Okay, so now then this is the one that most people commonly get confused with, but you all will not, because you're awesome. Okay, so ionization involves what? Covalent, not ionic, compounds dissolved in water. Water is and solvent. The only change is
transfer of a single hydrogen ion.
yes. Okay. So let's do a couple of these reactions.
And what is our first definition of acid and recognizable acid?
So your first definition of acid is something that releases hydrogen, releases H+. Okay. There's 2 ways. When you talk about H+, it's commonly called hydronium. And it can be written 2 ways. It can be written as H+, or it can be written as H3O+. Either one's correct. They both mean the same thing. So you'll commonly see this notation. You'll also commonly see just a hydrogen there. Okay. So if you start off with this one, and it's not fair because that's being used to cheat, but if you're starting off with this one, what's going to make this different is the water is there solvating, but it's also there as a participant. It's also there reacting. So what's happening is, he made a boo-boo here. These are all supposed to be aqueous. If they're not, they're actually just salts. Now then I went ahead and gave you that first one. But if it is a strong acid, which some of these are and some of these aren't, if it is a strong acid though, it will have a one-way arrow. These are your strong acids. This is why I just put this up here. If it is not one of these guys, it will have a two-way arrow. So a competing reaction in both directions. Okay, we're gonna have one of those in just a second. But because this is nitric acid, it's one of your strong acids, single-way arrow. Goes to completion. This hydrogen is releasing off this nitrate. The only guy it has to come to is that water. It's the only other reactant that's there. So it's going to release, come over to the water. It's going to add up to this water here. Now this water has one extra hydrogen and one extra positive charge in what it started with. And that nitrate, having lost a hydrogen, is now negative and also aqueous.
Sending.
Okay. Now HBr is going to be the same, strong acid, okay? So reacting with water, this should also be aqueous. All these acids down through here, make sure you put an aqueous notation next to them. Reacting with water. One-way arrow because we're still dealing with a strong acid. So what that's going to make there is that's going to make hydronium. And the only portion you have left of that is the bromide. I'm actually going to move this up a little bit. So you can see both of them. So now if you look at a couple that are weak, so what about this hydrofluoric acid one here? We just talked about that one. It's a weak acid, right? Weak acids have weak dissociations. Two-way arrow. Okay, it's the first time we've really talked about a two-way arrow, but it's a two-way arrow here. This hydrogen's still going to releases and goes to the water. Remember when we talked about fluorine and how super electronegative it was? Right? It's our marker point for every single thing. Well, what actually happens in this case right here is that fluorine wants a buddy so bad that it will come back into this water, strip that hydrogen back off, and go back. So you have a competing reaction in both directions. Okay, you don't have a strong enough acid for it to completely dissociate like we had down here, so you got this two-way arrow. What about these two? They can be strong or weaks? Weak. Both of them will be. So both these are going to be weak acids. This, I don't know if you can see this, but this is the same as this. This has two carbons, carbon, carbon. This has four hydrogens, 3, 4, and 2 oxygens. This is the same way as writing the same thing. Monday we'll talk about this. This is just the organic way of writing this. So when you get done with Chem 1 and Chem 2, and if you have to go on to organic, this is the organic way of writing acetic acid. This is the inorganic way of writing it. And the inorganic way, all it does is it shows you the acidic hydrogen at the end. The inorganic way shows it at the beginning. The hydrogen that is by itself is the hydrogen that would be pulled off. We're not pulling one of those three hydrogens out. Either way, we're not pulling one of those three. We're pulling that lone hydrogen by himself. So these will actually have the same type of reaction. I'm going to go through it a little bit quick, but it will have a double arrow. It will form hydronium, and in this case it'll form C2H3O2 negative. And then down here, same exact thing. Same exact thing for me. Okay. Any questions about those? The way you determine two-way arrow over a one-way arrow is your strongs. Your strong acids and your strong bases will always have a one-way arrow. They're strong enough that they can push the entire reaction to completion. Your weak acids do not have the brunt force to be able to do it. So your weak acids and your weak bases will have a two-way arrow. Okay? So your strong acids, the part that goes in this column right here, is going to be these 7 strong acids. So sulfuric, perchloric, chloric, hydrochloric, hydrobromic, hydroiodic, and nitric acid. Okay, that's your 7 strong acids. So they go in your strong acid column. Everything else that's not one of those 7 strong acids is a weak acid. Okay? Got to know that. It means that it's at equilibrium, it's trying to compete back and forth. So what you have happening here is once this breaks apart, once this hydrochloric acid breaks apart, this chlorine does not want to try and pick back up a hydrogen and go back across. That reverse reaction does not happen. Okay, but in the case of this hydrofluoric, what is happening there is this chlorine is wanting a hydrogen back, and it will get it, and it can get it back. So just as it gave the hydrogen away to start with to the water, it'll get it back to come back across. So when that hydrogen comes back to that fluorine, what you make coming backwards is more hydrofluoric acid and just neutral water. And they're oscillating back and forth. Some of this is breaking apart, some of that's coming back together.
So like a continuous thing?
Yeah, it'll eventually stop, but from the moment you put the weak acid in the water, it'll start, and at some point there'll be a certain amount of this, then a certain amount of this. And then you shake the beaker a little bit and it'll start moving again. So if you give it no kinetic energy, everything's eventually going to slow down, but the slightest bump in energy, so if the room temp goes up, it's going to start going back and forth again. We just put it there because it's constantly changing.
But what makes the weak acids not be able to push the reaction?
They're just not, they like their hydrogen too much. For right now, think of it like that. They like their hydrogen too much. So they'll give him away for a little bit, and then they want him back. When you get towards the end of this chapter, you're going to see what's happening with these oxygens. When you have a lot of oxygens around that center atom can't hold on to that hydrogen very well. How well does fluorine do of holding on to electrons? The best, right? He does it better than anyone else. He's the most electronegative, has the highest electron affinity. So when he leaves with almost a total negative charge. And if you have something positive floating around there, he's going to hold on to his electrons best. He's going to strip that positive away from whoever he's holding on to. Imagine it like a magnet. He's going to do it better than this guy will. Chlorine is not as electronegative as fluorine, so it'll let the hydrogen just float out there and just leave it alone. But that guy wants it back, and it makes him feel better to have it back. Carbon will do the same thing to fill back its octet. Doesn't want to give it up. Okay.
Also on the sheet it says that there's a second definition of phase. What is that? What was our first one?
So your first definition of an acid is going to be your
I'll
Lewis
do the
Bronsted.
acid, but I'm talking about the base.
Oh, well, there's one of each on there. It has acid and then base. Are you talking about the previous page?
Yeah.
Okay.
Are you talking about the first definition?
This one?
Or second? The
So your first definition of base is something that accepts a hydrogen. Something that accepts a hydrogen. Something that accepts that H plus. And your first definition of acid is something that releases that hydrogen.
What about just the second definition of base?
So your second definition of base needs to change to take into the account that now you've got things that can go in each direction. So it doesn't necessarily have to accept the hydrogen all the time. It can release it and then accept it back. So you really had two bases in this one, right? Let me scroll up. You really had two bases here. I can explain it to you, but someone help me out on how he worded that. So what's happening with this one here is you've got two bases that are happening. I'm not going to fill everything else in, but just to illustrate the point. Who is accepting the hydrogen from on this left side? Is the hydrofluoric acid accepting another hydrogen, or is the water? Water. So over here, this is acting as the base. It's accepting the hydrogen from that acid. Now, who's accepting the hydrogen from this side to go back? The fluoride. So now this is the base. Does that make sense? You don't necessarily have the same base on either side. I don't know exactly how you worded that in class, but that's the best way to explain it to you. Is it's something that will conjugate and change. So this is the base, that's the conjugate acid, because now it's giving up the hydrogen. This is the base, and there's its conjugate acid when it has the hydrogen. I don't know how he worded that on your exam study pack. But your base is always the thing that accepts the hydrogen, no matter whether you're dealing with a one-way arrow or a two-way arrow. It's always your acceptor of hydrogen. Okay, there's where he just exactly what I just showed you. The conjugate base pairs here at the bottom. So that would be what we just did right there. Scroll back up and put it on hydrofluoric. So if this is the acid, then this is the conjugate base to that acid. And if this is the base, then this is the conjugate acid to that base. Okay, and that's just moving back and forth between who's accepting and who's releasing the hydrogen. Is that better? Okay. So then we have what's called polyprotic acids, in which you have multiple hydrogens that can release. So you'll have multiple ionization levels. So is this a weak or a strong acid? Is carbonic acid a weak or a strong acid? Weak? Mm-hmm. So we're gonna, when we put this in water, the people who do this best is the Coca-Cola bottling company. Makes your soda nice and fizzy and makes your mouth burn. So you got this acid, you dissolve it in this water. Because it's a weak acid, you get a two-way arrow. You can only release one hydrogen at a time though. Well, that's a problem because we got two here. So that first hydrogen we release makes one formula unit of hydronium. And then what you have left still has one hydrogen and the carbonate, but it's now got a negative charge. Okay, so then what you're going to do is you're going to have one more step. of ionization. Much weaker, but there's still another step. So this percarbonate or bicarbonate is going to react with another water molecule, very weak this time. It's going to make a little bit more hydronium and then just a plain carbonate anion. Okay. Anytime you're doing ionization is the release of a single hydrogen. Single. You can't do both of them in one step. That water can only take one hydrogen at a time. You need a completely separate water molecule here to take that second hydrogen. Okay? What about this phosphoric acid? Well, it's going to have 3 levels of ionization. The first one is going to give you one hydronium, and what's left of the acids, the H2PO4 negative. If I'm not notating these with aqueous, please catch me and tell me. The only thing that's liquid, the only thing that should be liquid in this is all the water. Everything else it's producing is aqueous. Then your second level is going to be starting off with this piece and removing another hydrogen. We're still not done yet. Still have one more hydrogen we can take off. So those would be the polyprotic dissociation reactions for phosphoric acid and for carbonic acid. So for as many hydrogens as you have in front, you're going to have that many ionizations to break each one of those hydrogens off. Okay. Now we have something very interesting, a term very interesting that comes up here called amphoteric. So an amphoteric substance is something that we talked about a little bit in either the previous chapter or the first part of this chapter. And that's something that's actually an intermediate. So looking at both of these, let's start with the carbonic. What's something that appears on the right in that first reaction and then appears on the left in this second reaction? This guy, right? Right there. These are intermediate. If we were going through this reaction and doing some calculations, we'd use him as the ferry point, right? What's also interesting about this guy, if we pull him out to the side here and look at him, he has a negative. So because he has a negative, he can pick up a hydrogen, right? This guy can pick up a hydrogen and come back across to be his carbonic acid brother. But he also still has a hydrogen, so he can lose one more hydrogen. So something that can both lose and gain hydrogen is considered amphoteric. Okay? So you've got 2 amphoteric things in your phosphoric acid. You've got one here and one here. Okay, so H2PO4 negative is amphoteric, and so is HPO4 negative 2. Both of those are amphoteric. They still have hydrogen, so they can still lose, so they can make things more acidic, but they also have a negative charge, so they can pull in hydrogens and make things less acidic. Water. The exception is water. Water has hydrogens to lose, but it's the guy that's going to be acting as the base. It's never going to give up any more of its hydrogens than what it started with, right? Do you see water going down to just one hydrogen? It'll go up to 3 and then back down to 2, but it'll never go down to 1. It will not be the guy to lose 1 and then come back. Okay. Okay, so hydrofluoric acid. So since we're talking about ionization, you're talking about hydrofluoric acid reacting with water. It's a weak acid, so you're going to have a two-way arrow. You're going to make hydronium and fluoride anion. Okay. You've got 3 hydrogens on the left, 1 fluorine and 1 oxygen on the left. You've got 3 hydrogens on the right, 1 fluorine and 1 oxygen on the right. On this side you have no charge. On this side you have a positive and negative that cancels out, so you have a 0 total charge. Okay? Now this is the first base we've had here, and this is the first weak base we've had come up. So ammonia will actually strip a hydrogen from water. Watch this. Water is a weak base. I'm sorry. Water is a weak base, but your ammonia is a weak base. Weak base is two-way arrow. This guy, right here, weak base, he's going to accept a hydrogen. The only guy he can accept a hydrogen from is from that water. When he accepts that hydrogen, what it makes is an ammonium. And what's left behind there is a hydroxide. What is amphoteric and what is not? Is the fluoride amphoteric? Does it have a hydrogen? Can it lose 1 more? No. This guy's not amphoteric. It's that guy. Does he have a hydrogen that he could lose 1 more, and is he negative? Yes. So the only guy that's going to be amphoteric here is the hydroxide. If you had something that was a super strong base and could dissociate a base, I haven't done anything yet, but if you had something like that, it could strip that other hydrogen away.
Why wouldn't the NH4 be amphoteric too?
Can it
Oh, it's not negative.
Can it pick up 1 more hydrogen? It has the ability to lose 1 more and go back, but it doesn't have that negative. Think of it that you've got to be negative to entice something positive. Okay, you've got to have that negative charge.
I thought it had to start with the hydrogen.
It does. This originally, it's got 1 hydrogen now and 1 oxygen, but it originally started with 2.
Okay, sorry.
Mm-hmm. This guy picked up a hydrogen. If he'd have still been negative, he could have attracted 1 more, but he can't here.
Okay.
This equation right here, it's called the autoionization of water. Okay, it is very important. So I'm going to write it in a big tissue.